Hey everyone, welcome back, and today we're going to be doing something a little bit different from my usual style of videos. Usually I'll go over a DSA type leak code problem about programming in technical interviews for FANG companies, but today we're going to be going over something a little bit different. More specifically, we're going to be doing something in the field of mathematics, which is very closely tied to the field of computer science. More specifically, we're going to be talking about limits, which is a very major and core concept of calculus. And note that, again, limit is a very fundamental concept, and you have to be familiar and comfortable with limits to do well in other topics in calculus, right? So what exactly is a limit? Before we actually get into the formal definition and how it actually works in all of those operations, let's just take a quick function, for example. Let's say we have f of x. Could call it y, it doesn't really matter. Let's say it's equal to 1 over x. This is a parent function for the rational function. It's called a rational function, also known as a hyperbola. So if I were to do a quick sketch of this graph on the Cartesian plane or the coordinate plane, you'd see that it looks something like this. Again, I said quick sketch. This isn't a graph. Obviously, it can be a little bit more accurate, but for some key points on this graph, this is going to be 1, 1, if you really want to know that, and this is going to be negative 1, 1, and again, if you want a better, more accurate representation of this graph, feel free to just go on Desmos and graph y equals 1 over x. It's going to give you a perfect, accurate graph of how that would look like. Again, this is simply just a quick sketch of how that would look like once we have that graph. Now, there's two very important things to know, okay? The first thing is we have two asymptotes. What is an asymptote? If you recall, an asymptote is going to be a line that isn't actually part of the domain or range of a function. It's a line that the function gets infinitely close to or approaches but never actually hits. In this case, our two asymptotes are going to be x equals 0 and y equals 0. Right? Why is x equals 0 an asymptote? Why can't x equals 0 be part or a coordinate of x in this function? The reason why is if I were to go ahead and directly substitute x in this function, I'd see that I get 1 over 0. Everyone knows that you cannot divide by 0. It's undefined. It's breaking the rules of mathematics. And so that would give an output of undefined, which we obviously can't have because we can't plot that on a coordinate plane. Okay, so x equals 0 is not part of the domain of our function, and so this would not, or rather this would be an asymptote of this function. But why can't y be 0? Why is y equals 0 not in the range of our function, or in other words, not in the potential outputs or y values of our function? The reason why is 1 over x is never going to yield an output of 0. And if you were to analyze that graphically, you'll see right here that the function is getting closer and closer to this horizontal line, y equals 0. It's getting closer and closer to the y-axis, but it's never actually hitting the y-axis. Y actually never becomes 0. Again, as x gets larger and larger on the right-hand side, as you can see, as x gets bigger and bigger, our y values do get smaller and smaller. This function is decreasing on this interval. However, it never actually does hit 0. Although the function is decreasing as the x values get larger, the y values decrease. We never actually hit a value of y equals 0. Y simply cannot be equal to 0. It's simply not part of the range of our function, right? That's a very important thing to know. But this is exactly where limits actually come into play. We know that obviously y equals 0 is not in the range of the function as we discussed, but how do we get infinitely close to 0? What values should x be approaching to actually get a value that we can kind of approximate or approach to 0? If you really were to analyze this graphically, you'll see as x gets larger and larger, more to the right-hand side. Sorry, that's a horrible representation. Let me just get my eraser. Oops. This is a new UI for me as well. Anyways, okay. So as x gets larger and larger to the right of the coordinate plane, my y values are getting smaller. As x goes up, y goes down. So logically, if x were to hit infinity, could I conclude that y were to go to 0? And let's take a quick algebraic example to see why this claim could potentially be stated. Again, I'm not saying it's true or false. I'm just kind of throwing out this claim for you guys to think about. Let's say first that x is 1. We know if we were to plug in 1 to our function over here, simple, we get 1 over 1. That's 1. Okay, that's relatively small. Obviously, we have a lot of larger and a lot of smaller numbers. But what if we had 1 over 10? Suddenly, that's 0.0 Or sorry, 0.1. Sorry about that. That is a little bit smaller than 1. What if we had 1 over 1,000? Okay, that's 0.001. Okay, that's pretty small. What if we had 1 over a trillion? All of a sudden, that's 0 point a lot more zeros, 1. We have a lot more zeros in this gap. 1 over a billion, or rather a trillion, is a lot smaller than 1 over 1, or 1 over 10, or even 1 over 1,000. So as you can see, as our x values in the denominator get larger and larger, our y values get smaller. 1 over 1 is just 1. 1 over 1,000, 1 over 10 is just 0.1. 1 over 1,000 is 0.001. And 1 over a trillion is going to be like 8 or 11 zeros. That's insane. That's a very small number, right? At least relatively, right? What if we had 1 over, like 99 trillion? That would be even smaller. That would be even lower of a y value, or an output, if you will. So can we conclude that 1 over infinity, as x gets larger and larger and hits infinity, can that be 0? No, obviously it can't be 0. Again, infinity is just a concept, and y equals 0 isn't even in the range of this function. This is a completely false statement, but that's exactly, again, where limits come into play. We say in calculus the limit as x gets closer and closer to 0. So as my x values get larger and larger, get closer and closer to the maximal value of infinity, the function's y values, or output values, get closer and closer, or effectively hit the value of 0. And in calculus, it's a pretty weird looking annotation. It's kind of scary at first when you look at it initially, but it can be pretty self-explanatory once you solve a few problems involving limits. The way this is actually defined, or the formal notation of limits, is we're going to say LIM, kind of like a short form of limit. Underneath, we're going to put the value that x approaches, so the limit as x approaches infinity. And then we have our function 1 over x. The limit as x approaches infinity is going to have a value of 0. Because again, like we discussed just now, as our x values get closer and closer to 0, our y values get closer and closer to 0, and so we can approximate this limit to be equal to 0, right? So that's just the basic of limits, or the basics of limits. This is a very fundamental concept, and of course I haven't gone over more limits in more depth with harder concepts and examples. And this is just a very basic example of how limits work. Sorry if you guys can't read my handwriting. I'm not a very good drawer. I'm not very artistic, but this is a simple depiction of how limits really work and how we can really kind of define a function over a certain interval to see if it's increasing or decreasing, and see what its output values get closer and closer, or approach as our x values approach a specific value. And this is the formal notation of limits in calculus. Okay, that was a horrible O. It's okay, but this is just the formal notation of limits. So if you guys enjoyed this solution and learned something new, please consider liking this video, and just feel free to go on Khan Academy or just Google limits in general. Try to graph 1 over x on your own, and I'll give you a quick challenge problem. Find the limit as x approaches negative infinity. Okay, I'll just quickly give you guys that quick exercise. Try to find that on your own. You can interpret it graphically. You can kind of write out some algebraic examples as well, but try to find that limit out as a quick exercise. So again, if you guys enjoyed this lesson and learned something new in the field of calculus, more specifically limits, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.